Today, I'd like to talk about our paper. The title is Strict Stealth Walking of Legged Robot, formed by 4 parallelogram links and equipped with wobbling mass and reaction wheel. I am Fumihiko Asano from JIST, Japan. We have proposed the method of stealth walking that avoids the loss of kinetic energy at landing of the forefoot. The original purpose of starting the study of stealth walking was to realize a highly stable legged locomotion robot that does not have active ankle joints, but can start or stop walking movements at any instant. Through our early study, it was found that stealth walking is an effective method for achieving non-slip walking motion on low friction road surfaces. And the main issue was then moved to the problem of how to reduce the horizontal ground reaction force to 0, rather than starting or stopping walking motion. Strict stealth walking, SSW, is stealth walking that strictly maintains the horizontal ground reaction force at 0 during motion. According to the method of SSW, a point-footed walker can stably walk on a zero friction road surface without sliding. Based on the above problems, in this paper, we consider not only the realization of SSW, but also a general-purpose legged robot model and its control method that can freely stop walking motion even on a frictionless road surface. In this paper, we use the concept of combined rimless wheel to realize a legged robot that can start and stop walking at any moment. This movie shows the experimental passive dynamic walking of a prototype combined rimless wheel. 2 identical 8-legged rimless wheels are connected via a rigid body link. The rear and fore legs are connected via rods, and their movements are completely synchronized. Since the rear leg, the foreleg, the body frame, and the floor form a parallelogram link, the control torque around the rotational joint can be used as the ankle joint torque. In this paper, we propose a novel legged robot model that applies this property. This figure shows the overview of the legged robot that walks on the frictionless road surface. This model looks like an 8-legged rimless wheel, but it is the same as a combined rimless wheel with a very short body frame. It is assumed that the 2 8-legged rimless wheels have a symmetrical shape in which the relative angles of the adjacent leg frames are alpha equal pi over 4 radian, and that their end positions are connected by massless rods to always form 4 parallelogram links. In the following, we call the parallelogram link filled with pink color the stance leg, the massless rod of it fitting the floor, the sole, and the ground contact points of the rear foreleg, the rear forefoot. An active wobbling mass that can move along the body frame is mounted on it, and this is controlled to maintaining the horizontal ground reaction forces at 0 during motion. The greatest feature of this model is that it is possible to control the stance leg motion and the GMP independently of each other. Figure 2 left shows the coordinate system of the robot. Here, xg is the foot position of the rear rimless wheel, and x prime, g prime is that of the fore rimless wheel. L1 is the leg length or radius of the rear rimless wheel. L2 is half the length of the body frame. L3 is the leg length or radius of the fore rimless wheel. And LW is the length or position of the wobbling mass on the body frame, and this is one of the state variables. θ1 and θ3 are the absolute angles of the rear and fore limbless wheels with respect to the vertical direction, and θ2 to θ4 are those of the body frame and reaction wheel with respect to the horizontal direction. Modeling. The robot has 7 DOF, 3 constraints, and 3 control inputs. Let Q be the generalized coordinate vector. The robot equation of motion then becomes like this. Here, SU is the control input vector like this. JCQ dot equals 0 describes the velocity constraint conditions. Here, G dot equals 0 and G prime dot equals 0 describes the contact condition of the rear and fore feet. θ1 dot minus θ3 dot equals 0 describes the constraint condition due to the massless rod. According to this, the stance leg can always form a parallelogram link on a zero friction rod surface. The robot has 3 control inputs. U1 is the rotation torque between the rear limbless wheel and the body frame. U2 is the rotation torque between the body frame and the reaction wheel. And U3 is the translational force for telescopic motion of the wobbling mass. Due to the parallelogram link structure, the body frame is always kept in the horizontal posture when the sole is fitted to the road surface. And it is easy to control the wobbling mass in the X direction to avoid sliding. In addition, since the control torque U1 can function as a rotation torque around the ground contact point, it would be possible to achieve a sudden stop of walking motion. For generating a stealth walking gait, the stance leg motion must be preferentially and strictly controlled so that the forefoot can land on the ground without causing kinetic energy dissipation. In this paper, however, we consider to generate a SSW gait more easily based on the sinusoidal motion of the wobbling mass. First, we set the length of the wobbling mass, LW, to the controlled output. Second, we set the X position of the rear stance foot, X, to the controlled output. Third, we set the angular position of the reaction wheel, θ4, to the controlled output. As long as we can control LW and X, it is possible to generate a SSW gait. So we ignore the control of θ4 first. In this paper, we consider to apply PD feedback control for generating the sinusoidal motion of LW and maintaining X at 0. Following these 3 target conditions, we can determine the control input U like this. The system parameters were chosen as the values listed in Table 1. Animation of the generated SSW gate on the zero friction road surface, we can see that the 2 vertical ground reaction forces always have opposite signs to each other. Figure 3 shows the simulation results of SSW without using the reaction wheel. From figure 3D, we can see that the vertical ground reaction forces have become negative during motion, This means that the rear or forefoot would take off, but we ignored it in the simulation. So the obtained simulation results are unrealistic. In order to solve this problem, we then consider to use the reaction field to control the vertical ground reaction force or zero moment point. In this paper, the target condition is set as Fg is equivalent to Fg prime. This can be specified by this equation. If this condition is achieved, the GMP will always be positioned at the central point of the sole, like this. Following these three target conditions and solving for the control input U, we can determine it as phi inverse gamma. Animation of the generated SSW gate with control of the reaction field. According to the modified control method, the vertical ground reaction forces are always controlled to the same value during motion. Figure 4 shows the simulation results of SSW with control of the reaction field. We can see that the generated motions, except the ground reaction forces, are the same as before. By appropriately setting the target initial angular velocity of the reaction field, it can generate a stable limit cycle. Finally, we discuss how energy efficiency improvements can be achieved by attaching elastic elements, as in Figure 6. Figure 7 shows the analysis results of specific resistance with respect to the three elastic moduli. The system parameters, except for the elastic moduli, were chosen as the same values listed in Table 1 again. In each case, the change in specific resistance due to one elastic modulus was analyzed, and the values of the other two elastic moduli were set to 0. The analysis results show that there exists an optimal modulus for minimizing specific resistance in each case. By using the elastic elements with optimal moduli, the specific resistance was reduced to 2.19244. This is about half of the original value. Conclusion. A novel legged locomotion robot that consists of two identical 8-legged rimless wheels with an active wobbling mass and a reaction field was proposed. By appropriately controlling the wobbling mass and reaction field simultaneously, a stable SSW gate has been successfully generated on a zero friction load surface. A significant improvement in energy efficiency was achieved by using elastic elements. Future work. Investigation of sudden stop of walking motion by making use of the advantage of surface contact between the sole and the floor. Investigation of a method for generating a limit cycle gate based on a completely stationary standing posture, and extension to stair climbing motion generation. That's all. Thank you very much for your attention.